Hey, good morning. Can you hear me?
Yes.
Okay.
Can you hear me? Okay.
Professor Ma, do you
Yes,
want
this.
to share your screen?
Yes, this is okay. Mhm.
Nice, good.
Okay, let me share my screen, right? So, can you see the
Yes.
screen?
Okay.
Okay.
Okay. That's a few minutes.
In full screen mode.
Yeah.
It's good.
Just a few minutes.
That's good. Okay. Sure.
Okay. It's time to start. Yeah, sorry. Okay. Good morning. I'm Ge Li from Peking University. I'm the host of today's keynote speech. This is the third day of our conference. Different from previous years, this conference is held online. Although we cannot have on-site and more on-site communication as usual, it also provides an opportunity for more people to take part in our conference. I hope everybody have a good, different but good experience. Okay, let's start today's keynote speech. Our keynote speech today is from Professor Ma Xiaoxing of Nanjing University. Xiaoxing Ma is professor and the duty head of the Department of Computer Science and Technology at Nanjing University. He received his doctorate degree in computer science in 2003. His research interests include self-adaptive software systems, software architectures, and quality assurance for machine learning models used as a software component. He co-authored over 100 peer-reviewed papers and served in technical program committee various international conferences. He had received 2 second prize of the National Science and Technology Progress Award of China and several Best or Distinguished Paper Award. Today's topic of his speech is operational software quality assurance for DNNs in the field. Let's start. If you have any question, please leave a message in the chat area. Okay, Professor Ma, let's start.
Okay, thank you, Ge. Okay, good morning, everyone. I'm Xiaoxing from Nanjing University. I'm very glad and honored to have this opportunity to share with you our recent work and idea on operational software quality assurance for DNNs in the field. Actually, the word in the field is a little bit exaggerated because we didn't drive a Tesla on the road to test its software. But anyway, we will tell you why we say so, okay? So this is the outline. In the first part, I will talk about the subject, that is the well-trained DNN models as the subject of quality assurance, which is quite different from conventional software quality assurance and requires some special considerations. And then we are going to talk about a concrete work that is operational accuracy estimation to tell how well a DNN model will work in operation domain, which is corresponding to conventional software testing. And then we need to improve the usability of DNN models through operational confidence calibration, which is corresponding to software debugging in the conventional settings. Okay, this work are based on the joint work with my student Zenan and other colleagues. Okay, now the topic of deep learning is so hot that we software engineering researchers also need to do some research on this topic. Otherwise, no student will join us, right? So, but anyway, it's not deniable that deep learning has achieved great success in some difficult tasks such as image classification, natural language processing, and some chess such as AlphaGo. And the adoption of deep learning models is increasing in some important application domains such as self-driving cars and AI-aided medicine. And so the trained DNN models are becoming integral parts of complex software systems. As the director of AI at Tesla says, it becomes software 2.0. So we have to consider the deep learning models in the software engineering. Okay, but here is a big but. We all have heard of many tragic accidents of the Ubers and Tesla, and some stories of stupid intelligent systems and some misuse of deep learning. As really once put in a comment article in Nature, one often overestimates how well the model will do in practice. A common situation is that deep learning researchers often train their model in the lab with their data and to test the trained model on the test set. And with some black magic, they have a very good performance model. But unfortunately, when the model is delivered to our software engineer, we apply these models in the operational settings. Usually, we will find that the model is very poor. So the problem is that more or less there is some divergence between the data in the lab and the data in the field. And this is sometimes called distribution shift or data set shift in the machine learning literature. So as a software engineer, we have to consider the quality assurance of DNN models to deploy them in the field. But unfortunately, we cannot directly apply our conventional quality assurance techniques on the DNN models, because DNN models is intrinsically inductive, while our conventional software is basically deductive. By induction, here is an example. For example, we observe a sparrow can fly, and a pigeon can fly, and a duck can fly, and so on. So we predict probably every bird can fly. This is induction. Deduction is that, for example, we know die is a man, so we conclude. So the induction is intrinsically uncertain. It's not like deduction, but our conventional software is basically deductive, and also it's quality assurance. For example, the correctness of a program means the program will satisfy its specification, and the specification states the assumption on the input that the program can make. It's the program's right. We often call it preconditions. And it also says the guarantees for the output that the program must provide, that is post conditions. This is the program's obligations. So a correct program must produce an output satisfying the post condition for each input that satisfies the precondition. So here we have a deduction that every single error-inducing input falsifies the correctness. This is a deduction. So the software testing is simply hunting for error-inducing input. And the debugging is to locate and fix the defects that causes errors. This has some underlying assumptions. First is certainty. That is, each error-inducing input means a bug. And second is the independence. That is, the correctness can be verified against the specification, independent of where the software is used. And the interpretability, that is, the behavior of a program can be interpreted with the concrete code. And so defects can be located and fixed locally. And the incrementality, we fix an error means a step of improvement and better quality of the software, okay? But unfortunately, all these assumptions break down for DNN models. When we talk about a trained DNN model, we first have a labeled data set, and we hold some data for testing. And we use the rest data to train the model and to try the trained model on the test data. If the performance is good, and we put the trained model into application. Here, what's learned is a probabilistic model. We only know its prediction accuracy on the test data, but we expect the model to be general and to work well in operation, but there is no guarantee, okay? Here, no promise is made on the correctness on each input, and the performance is measured statistically. So this is the uncertainty, right? And the scope of the generalizability is unknown. Actually, it's unspecified. And, there is no such sense of specification, okay? So that's the quality depending on the operation environment. So there is no independence. And currently, there is no satisfactory logical interpretation of the DNNs model on each individual inputs. So there is no interpretability. And correcting individual error outputs, so no incrementality. So this means that conventional software quality assurance activities such as debugging and testing are not directly applicable to the DNN models. But anyway, we still need to evaluate the DNN model's actual performance in the field and to improve its usability. To do so, we need a new approaches that are statistical, operational, and efficient. By statistical, we mean that we need to focus on statistical measurements, but not on hunting for individual prediction errors, right? Because the number of adversarial or error inputs says little about the quality of the model. Actually, we have published a paper arguing that structural coverage criteria for neural networks are actually often misleading, because they are still hunting for individual prediction errors. And by operational, we mean that we should focus on the data in the field, but not the data in the lab. Here is a real-world example. We are going to train a model to diagnose the tenosynovitis. This is a disease on the finger, which is often found among the programmers. And in the lab data, we achieved accuracy around 95%. But on the actual field data, the accuracy drops to under 60. So generally, the divergence between the operation and the training data is almost unavailable. More or less, you will have this divergence. And because the DNN model has no specification, so quality not referring to its operational domain is actually meaningless. So when we talk about the quality assurance for the DNN model, we need to take the operation environment into consideration. Okay. And finally, the quality assurance must be efficient, because different from the machine learning or transfer learning settings, we cannot assume we have many data, because the original training data is often unavailable, because today we have many property and privacy concerns, especially the European Union's GDPR rule will prevent most of the sharing of the training data. And we also do not have many labeled operational data. You may be able to collect unlabeled operational data, but labeling them can be very expensive, because sometimes you need to do some, for example, intrusive biopsy operations to label a radiology image, or to do some destructive testing. So labeling operational data could be very expensive. So we have this overall framework. So we have a training data set, and we produce a trained model, a DNN model. But before put the model into operation, we need to do some operational quality assurance with the operational data. To reduce the cost of the labeling, we need first select from the unlabeled operational data to select a very small data set to label. And with this selected data set, we can do operational quality assurance activities. And with these assessment and adaptations, we can put the model into operation. Okay. So this is the first part. And the second part is the testing, that is to estimate the actual accuracy of DNNs in a given operational environment. The problem is that giving a trained DNN model and a set of unlabeled examples collected from an operational context, instead of labeling all these examples, we want to select and label a very small subset of it so that we can use this small data set to estimate the accuracy of the model on this particular environment with as small estimation error as possible. Okay. So we view the DNN testing as a sampling and estimation problem. So here we measure the model's actual accuracy in the field or in the operational domain as the expected chance of correct predictions. So the idea is to reduce the MSE, that is, we need an unbiased estimation with small variance with a given budget of sample size. It is quite difficult because it's a high-dimensional problem. It's quite difficult to improve over the simple random sampling strategy. The idea here is that to borrow the insight of structural coverage, because we software engineers are quite familiar with structural coverage, right? So, but as I already said earlier, direct apply the structural coverage guided testing on DNNs are often ineffective. So we need to reinterpret them statistically. Note that the aim of conventional software testing is to discover every error-inducing inputs, and the more, the better. And the aim of our operational DNN testing is to estimate the accuracy of the model. The smaller error, the better. So let's recall the idea of structural coverage in conventional software testing. So the basic idea is to partition the input space according to program structures, let it be a statement, function, operation, etc. And we want to achieve better testing sufficiency by covering more parts. The insight behind the structural coverage is that it achieves homogeneity and diversity. Homogeneous means that we want to partition the input space in such a way that for each part, either all or none of the inputs inducing an error. For diversity means that giving a budget of tests, we want to select a test input from the different parts of the partition. So this is why we believe structural coverage is effective, right? But now we need to do some statistics, and we need to reduce the variance. The basic technique is by conditioning. That is to find a random variable as a condition, which acts as the role of program structure in conventional testing. And the condition Z must be strongly corrected to HX. Here is the law of total variance. Let me first give you a simple example. Suppose you are going to estimate the average chance of a person being pregnant, okay? One can use simple random sampling. We just randomly select some person to ask them if they are pregnant, okay? Or better, because we know that pregnancy is closely related to the sex, male or female, and the age and the situation married or single. So one can better use his budget of sampling by conditioning on these variables, because these variables give us some information about being pregnant or not. So technically, mathematically, the variance can be decomposed into two parts. The first part is the variance not explained by the condition Z, and the second part is the variance can be explained by the condition Z. And the first part is actually the homogeneity. We want that for same Z, either all or none of the inputs will inducing an error. And for the second part, we need to systematically sample the Z so that we can have a representative sample of Z. So this is also homogeneity and diversity. So so we need to identify an observable factor Z, and it needs to be highly correlated with HX. That is whether the prediction will be error or correct. And we need to be able to sample Z efficiently. Here is a trade-off, because the budget of sampling is given. If you want more homogeneity, that means we need to the space of Z will be very large, and we will be less diversity in sampling Z. And if you want more diversity, and you have to sacrifice the homogeneity in the partitioning. Okay. So a naive approach to find a condition variable is that to use the confidence output of the model. The confidence is intended to give the chance of the prediction being correct. So if there is no divergence between the training data and the operation data, the confidence provides a very good choice for the condition variable. We can see this from the left side of the figure. But unfortunately, this is very sensitive to the divergence between training data and operation data. We can see this from the right side of the figures. That if we use the confidence as the condition variable, which is depicted as the red dots and lines, it performs much worse than the simple baseline approach, simple random sampling. Okay. So the way out is to rethink about the deep learning approach. A mainstream interpretation of why deep learning works is that DNN models are good at learning representations. Okay. Which should be more stable than the model's prediction capability. Okay, so to verify this case, we have some observations that the distribution of prediction errors are actually clustered in the representation space. By representation space, we mean the last hidden layer of the neural network, and this locality can be used to provide the needed homogeneity of the partition of inputs, the input space. So we choose the output of the last hidden layer as the condition variable Z. Okay, but we still have a difficulty, because the condition variable Z is still highly dimensional. It can be even more than 2,000 dimensional. Okay, so how to use a small sample with size with tens to hundreds of examples to represent a high dimensional Z? This is the curse of dimensionality. So our approach is to use optimization instead of sampling. So we need a small sample T, which will be labeled, and the whole, which is representative with respect to the whole unlabeled dataset Z. So our approach is to minimize the cross entropy between T and S. Okay. So here, the interesting thing is that we have made a statistical reinterpretation of the insight of conventional software testing. For example, we use feature representation to act as the role of program structure in conventional software testing. And the homogeneity becomes the locality of the feature space. And the diversity becomes the representativeness of the sample through cross-entropy minimization. Okay, here is the empirical evaluation. We measure the relative efficiency of our approach, which indicates the rate of saving in sample size, right? The baseline approach is just simple random sampling, okay? We have applied the approach on some widely used datasets and physically meaningful mutations to simulate real-world operation domain. And we also use some third-party transfer learning datasets. We have tried different DNN models from LandNet to VGG to ResNet. And the result shows that our approach always outperformed simple random sampling, regardless of the difference in the datasets, models, and sample sizes. And in conclusion, our approach saved half of the labeling effort. Okay, so this is testing to see how a model actually perform in the field. The next step is to debug, to improve the usability of DNN model for an concrete operational environment. So let's first think about the term debugging. What is a bug for a DNN model? That usually a bug is a case that software cannot keep its promise. Okay, but DNN models are intrinsically uncertain. So how could it be run? Because it never promises to be correct on any input, right? So it cannot be run. However, a DNN model usually gives, together with its prediction, a confidence value, which indicates the probability that the prediction being correct. So perhaps we can define a bug as a case that the confidence value does not reflect the actual chance of the prediction being correct. If we take this definition of bug, the debugging is to fix the prediction or fix the confidence or both. But fixed prediction often require retraining the model, which is usually infeasible because if we are using a third-party model, perhaps we do not have the original training data and we do not have many operational data. Actually, the accurate confidence is very important in real-world decisions. Let's consider this this case. We are going to diagnose, let's say, lung cancer with radiology images. We train a model. The model says that okay, this guy is okay. The image is benign and with high confidence. Okay. Let's assume the prediction is correct and the confidence is accurate and everything is okay. Okay. let's say, unfortunately, in this case, actually the image is management. Okay, it's not good. But let's say the model makes an error prediction here. But if the confidence is accurate, in this case, it must be low. So don't panic, because in this case, the patient will take confirmatory testing. So the damage is limited, even with the wrong prediction. If the confidence is accurate, okay. The third case is that it makes a correct prediction, but with inaccurate confidence. In this case, the patient will take unnecessary confirmatory testing. So it will cause some loss despite of the correct prediction, okay? So the worst case is that the model make incorrect prediction and give a high confidence. In this case, it will mislead the patient to ignore the cancer, and it will cause disastrous consequences. So we need to exclude these high confidence error predictions. So these high confidence errors are much more damage than low confidence errors. And if the confidence is accurate, even a poor model is partially useful because we can just take the high confidence output and reject the low confidence ones. So as Confucius said, to know what you know and what you do not know, that is true knowledge. So we want accurate confidence. But unfortunately, DNN models, the confidence is very sensitive to domain shift. Here is an example. We have a model trained on CIFAR-10, and on the CIFAR-10 test set, it only have less than 5% mispredictions in all high confidence predictions. But if we apply it to STL-10, it will have about a half mispredictions in all high confidence predictions. So we need to identify and fix inaccurate confidence for each predictions in the operation domain. So the problem of efficient operational calibration is that giving a model, a previously trained DNN model that is a classifier, and a set of examples collected from an operation domain, and we need to find a small set of labeled to label, and to use this small label dataset to find a confidence estimation function for M, so that it can tell us the accurate confidence for each input. The difficulty here is that we need to find a function instead of a value, because in the operational estimation of accuracy, we only need to find a value. Here we need a function, so the task is much more challenging. So the difficulty comes from the very limited data available and the high dimensional input. And this problem is a regression problem. We need to find a value, but not a 1 or 0 result. So our basic idea is to leverage the model's representative layer. That is, we make use of its representation learning capability. And we need to use the Bayesian inference to overcome our fitting. We cannot simply use many other regression methods that require many data. So we have to use Bayesian inference, okay? So the overall framework is like this. First, we take the representation space that is the last hidden layer of the DNN model instead of the original input space. And in this representation space, we make some clustering to make use of the locality of the arrows. And for each cluster, we build a Gaussian process. When we observe an arrow prediction or a correct prediction, we will adjust the confidence accordingly. So finally, we will have a much more accurate confidence function. So the reason behind using the Gaussian process here is that it works very limited data set, and it can make full use of the confidence learned by the DNN model. Although the confidence learned by the DNN model is inaccurate on the operational domain, it still provides us much information. So it can be used as a priori. And we can leverage the locality with the RBF kernel as this. And the Gaussian process also quantifies the uncertainty, which can be used to guide the sampling. This is somewhat like active learning. You may know that. We also made some empirical evaluation of this approach to see if it is effective and efficient. By efficacy, we want to see that is our approach generally effective for different tasks and how effective it is compared with other approaches. And the efficiency, we want to see if the approach be able to exclude the high confidence error predictions with very, very small amount of labeled operational data. So the settings is like this. We have many different data sets, including some third-party transfer learning data sets and some practically mutation-based data sets. And the models from small models to very huge models. We have RNN and CNN, and the tasks include the image classification and natural language processing. And the metrics is the Breyer score, which is the MSE for the confidence. And we also considering the cost-sensitive case to measure the loss due to confidence error. And the baseline is conventional calibration methods such as temperature scaling and blood scaling, isotonic regression, etc. And the result is that our approach significantly outperformed all the other calibration methods. We can see from this table that the read numbers are our operational calibration. Okay, and reduced about half of the loss due to confidence error. And the efficiency. We can see that with 5,000 examples, okay, VGG cannot be fine-tuned, you know, and inception also cannot be fine-tuned. But with only 10 of these data, we can reduce about 70 to 97% of the high confidence errors, with only about 10% of the minimal bound of labeled operational data that is needed for practical learning techniques to barely work. So this is very, very efficient, which is much better than our own expectation. The reason is that the approach identifies and find the false predictions very quickly. We can see from the curve of the red line that with very small sample size, we can reduce most of the high confidence errors. So, in summary, I like to say that with the increasing adoption of trained DNN models in real-world settings, their quality assurance become an urgent need and become a topic of our software engineering researchers. And DNN models are fundamentally different from traditional software. So their quality assurance needs to be statistical, operational, and efficient. And the representation learned by a DNN model is often effective, even there are some domain shifts, which can be leveraged to improve the efficiency of quality assurance, as shown in our work on operational testing and operational calibration. Okay, this is all I want to say today. So thank you. Any questions?
Thank you. Thank you.
Okay, thank you.
Excellent speech. Anyone has questions? You can type your question on the chat area.
Maybe I can start with one.
Okay.
Yep.
Yeah.
So this is from SMU. Really wonderful talk indeed. So I'm just wondering, so the calibration, I haven't come across this calibration idea before. So how does the calibration work? So you have some input, and then you first judge which region it belongs to, and then based on the trained function, you apply the function to, well, calibrate the confidence, I guess.
Yes. By calibration, we mean we have here, here, we use a Gaussian process. It's a regression problem, but with very small training data, because the training data is collected from the let's say operation domain.
Thanks, Professor Ma, again for his speech. Very wonderful speech. Yeah.
Okay, thank you.
Thank you. Thank you. And I think next we should have a few minutes break and then continue our conference. And I also transfer the host to the next session chairs. Thank you. Thank you again, Professor Ma.
Thank you.
Thanks for all the parties. Yeah, thank you. Thank you. Thank you all. Let's have a break.